es un profesor muy conocido en el medio de la matemática aplicada a nivel internacional y pues tiene un interés muy particular porque mezcla pues aspectos del álgebra lineal numérica, optimización, aplicaciones, tanto en matemáticas como en ingeniería, y tiene alrededor de 150 artículos publicados, 2 libros y uno en proceso que está escribiendo actualmente. Por supuesto ha dirigido varias tesis de posgrado y de licenciatura. Ha sido profesor visitante de varias universidades en varios lugares del mundo, en Asia, Canadá, etcétera. Incluso Brasil. También estuvo hace 40 años, 30 años, en Brasil, fue profesor visitante. Y precisamente fue en Brasil donde yo lo conocí, hace más o menos 27 años, ya tiene un buen rato. Yo era recién doctorado en ese tiempo, entonces bueno, pues tuve la suerte de encontrármelo por ahí en Brasil y pues desde esa época tenemos una gran amistad. Entonces, si quieren investigar más sobre el profesor, pues es muy fácil, se va uno a Google, ¿verdad? Y ahí ya tienen toda la información que quieran. Entonces no los quiero entretener tanto con la biografía de Biswa. Tiene muchos premios, etcétera. Entonces, bueno, si son curiosos pueden verlo por ahí, consultarlo. Entonces yo los dejo con el profesor y pues le doy las gracias por aceptar la invitación que le hicimos.
Buenas tardes. Yo no hablo español. Algunas palabras solamente. Disculpe. Por tanto, voy a cambiar en inglés. Well, first of all, I'd like to thank Professor Hector. As he said, that we know each other for the last almost 30 years. He's a good friend of mine, and I'd like to thank him for his kind invitation to come to this conference, give a short course, and now I'm giving this plenary address. And thank you for coming. Okay. As you can see that this is an interdisciplinary talk, blending computational mathematics, optimization, and 2 areas of mechanical engineering. Of course, the second one, the finite element model updating, is especially of importance to aerospace engineering. The active vibration control is, of course, of importance to mechanical engineering. So it's an interdisciplinary talk between blending mathematics, computational mathematics, and 2 areas of engineering. Okay? So let me start with the first one. If I have time, I'll go to the second topic. If not, that's too bad. I have lots of collaborators from all over the world. You know, as Victor told you that I like to travel. So whenever I go, I get some collaborators to work with me, and I love that. Okay, let me start with this big picture. Have you ever seen this picture before? No. This is the picture of Millennium Bridge on the River Thames in London, England. This bridge was constructed to inaugurate Millennium. An interesting fact of that bridge was that on the day of its inauguration, several hundreds of people came to see the bridge all at a time. And the bridge started rumbling. What happens? Well, I'll tell you what happens. Seeing this, the smart engineer of the bridge, he immediately closed the bridge. And then spending about few millions of British pounds, they did something and bridge started again. Now, what happened is the following. What happened is that this is something called, we already know, something called a resonance. Resonance happens when frequencies of some external force become quite close to the frequency of the vibrating of the structure. In this case, the external force was the weights of the human bodies, and the structure was, of course, the bridge. So this is one example, but there are many famous examples of resonance. For example, this is the famous bridge called Tacoma Bridge in the state of Washington, near Seattle. And it's a historical thing, okay? And there's an interesting story about this bridge. A professor from mechanical engineering from University of Washington in Seattle, he was the principal designer of the bridge. And he was so proud of that bridge that nothing can go wrong. No vibration can cause any damage to the bridge. So one day, gusty wind was blowing to the bridge. Seeing this, and the bridge was doing like this. Seeing this, the proud engineer professor, he ran to the bridge and stood there on his feet to prove to the whole world that his mathematics cannot go wrong. But unfortunately went wrong. And his life was saved at the last minute by a police helicopter. So again, this was caused by resonance. In this case, the external force was the wind. Okay? So resonance occurs when the frequencies of the external force become quite close to the frequencies of the structures. Okay? It doesn't happen very often, but it does happen. And we have seen many, many times it happens. Okay. So we are going to look into the mathematical aspects of this thing. Okay. And that's where the eigenvalue problem is coming. Okay. Oh God, I don't know what is happening. Okay. Now, how to control such a vibration? Well, the traditional way, and still very popular way, is very ad hoc in nature. Increase some damping in the structure. Every vibrating structure has stiffness, mass, and damping. So increase some stiffness and mass cannot be changed. So increase some damping in the structure, so the vibration stops. But this is an ad hoc way. You do that to control the vibration once. When it again happens again, you do it another time. So it is not a mathematical way of doing that. So a mathematical way of doing that is to use what is called active control. That's what I'm going to talk about. What is active control? Well, first of all, I have to talk about the eigenvalue problem of the model. Now, vibrating structures like buildings, bridges, highways, these are distributed parameter systems Professor Hector knows very well. These are partial differential equations with nonlinear boundary conditions from the Hilbert space. But in practice, what happens, these differential equations, these partial differential equations are approximated by means of a second order differential equation, okay, of this form, mx double dot t plus cx dot t plus kx t equal to 0, where m, c, and k are the constant matrices. M is the mass matrix, k is the stiffness matrix, and c is the damping matrix. X double dot t represents the acceleration. X dot t represents the velocity, and xt is the displacement. Okay. And the natural frequencies and the mode sets of these equations are governed by an eigenvalue, associated eigenvalue. The eigenvalue is called the quadratic eigenvalue problem. It's a mathematics conference, so I decided to talk about mathematics here. So there's an eigenvalue problem associated with that, and it's called quadratic eigenvalue problem. It's an eigenvalue problem of the pencil, lambda square m plus lambda c plus k, x equal to 0. Lambdas are the eigenvalues, x are the eigenvectors. Now, what is this eigenvalue problem? Well, we all know the standard eigenvalue problem, ax equal to lambda x, right? There is a generalization of this eigenvalue problem to a pair of eigenvalues, a pair of matrices, ax equal to lambda bx, where a and b are given to you, you have to find lambda and x. And this is another generalization to the second order case. So this is the eigenvalue where m, c, and k are given to you. You have to find lambdas and x's so that this equation will be satisfied. It's a generalization of the standard eigenvalue problem. And the eigenvalues of this matrix, the engineers call them natural frequencies. And the eigenvectors in engineering called the mode shapes. But for us, it's eigenvalues and eigenvectors. Now, how many eigenvalues are there for this problem? Well, if m is non-singular, each of them is n by n square matrices. If m is non-singular, then there are 2n eigenvalues and corresponding to n eigenvectors. Now, how do you compute these eigenvalues? Well, it turns out that it's not an easy problem. Well, one standard way to do that, you transform the second order eigenvalue, transfer the quadratic eigenvalue problem to a standard eigenvalue problem. And then you apply the techniques like keyword iteration algorithm to solve the problem. But this is not the right way to do that because it needs inversion of the matrix M. And if the matrix M happens to be ill-conditioned, then that idea doesn't work very well. In general, this is a quadratic problem, non-linear, and it's hard to solve. The state of the art is to compute only few eigenvalues and eigenvectors. By means of some projection technique, the large eigenvalue problem is projected in a smaller subspace, and then compute few eigenvalues and eigenvectors from there. And those are the ones which are taken as approximation of the eigenvalues and eigenvectors. And unfortunately, no numerical linear algebra book, no numerical analysis book, including the famous book by Golub and Van Loon, does not talk about this eigenvalue problem. Only my book does. Okay, because I included, by the way, some of you don't know that I have a book on numerical linear algebra and application, And Professor Hector has agreed to share the copies with you if you want. That book has a chapter on how to compute the eigenvalues and eigenvectors, few ones of the second order, for the quadratic eigenvalue problem. Excuse me, I have asthma and my tourism. So, the state of the art is to compute only few extreme eigenvalues and corresponding eigenvectors. So, the question arises, using only those few eigenvalues and eigenvectors, how can we solve the resonance problem? Well, I don't know. I'm going backward. What is happening? Okay. Yeah, this is the book I'm talking about. Yeah. Okay, so I just said that Professor Hector has a copy and he can give you the access if you would like to have a look. Okay, so the idea here is the following. We have to use some control force. This is that, I don't know whether some of you are familiar with the control. Oh, God. So the idea is the following. We have to use some control force. The control force will be required to control those resonant eigenvalues, the eigenvalues that cause resonance. Okay, the way we do that, we have to put a control vector u of t with some two unknown matrices f and g, and a control matrix B, and you put it back, so if you get a closed loop system of this form. I think lambda square is a typo, so you don't know that. So what happens that from the original second order differential equation, we now have a closed loop differential equation, differential equation with a control matrix B, which is known, but two unknown matrices F and G. So the problem is how to choose those two unknown matrices F and G. These are called the feedback matrices in control theory. Okay, so how to choose those two feedback matrices F and G in such a way that the few resonant eigenvalues will be replaced by suitably chosen ones, good eigenvalues, leaving the rest of them are unchanged, and the corresponding eigenvectors. Now, the thing is this, that the state of the art, as I said, can compute only few eigenvalues and eigenvectors. Rest of them are not known to you. So the technique here is, it's a difficult problem. So you have to choose the two control matrices F and G in such a way that this matrix, this is called closed loop system, this matrix has those few eigenvalues which are bad ones replaced by suitably chosen ones, good eigenvalues, keeping the remaining, say 2n minus p eigenvalues, p is the number, 2n minus p eigenvalues unchanged, and the corresponding eigenvectors. without knowing them. So you have to do some mathematical trick. And in mechanical engineering, it's called no spillover. You do the things in a way that it doesn't spill over. Well, it doesn't matter, but that's what it means. Any questions so far? Do you understand what the problem I'm talking about here? Yeah, eigenvalues and eigenvectors, both. Yeah, I want to change a few eigenvalues which are bad in such a way that the few eigenvalues, the bad eigenvalues will be replaced by good eigenvalues, on keeping all the remaining eigenvalues and eigenvectors unchanged. That's what I'm talking about. That is called the no spillover. Okay? So the problem is, it's a nice problem, but it's not an easy problem to solve. It is not an easy problem to solve. That is because that you don't know the large number of eigenvalues and eigenvectors which have to be kept unchanged. That's the problem. Okay. You have to do that using some mathematical tricks. So that's what I'm going to do. It's a hard problem, but we have a very nice solution. So this is the problem I'm talking about. So this is the quadratic partial eigenvalue assignment problem. So the problem is, as I said, find the feedback matrices F and G such that few resonant eigenvalues, say lambda 1 through lambda p, where p is much, much less than 2n, are replaced by suitably chosen ones, say mu1 through mu p, while the remaining 2n minus p eigenvectors and eigenvalues for this closed group pencil will remain unchanged. Okay? That's the problem. And it's a mathematical problem, difficult problem, but this problem is very much importance to mechanical engineering, to control the resonance in mechanical structures. So here, the lambda 1 to lambda p are the resonant eigenvalues. Those are the eigenvalues that cause resonance. So they have to be chosen, they have to be replaced by good eigenvalues, mu1 through mu p. Or you can ask, what are the good eigenvalues? We don't know that. The practicing engineers, they have some ideas how to choose the good eigenvalues. Which eigenvalues will not give you the resonance. Okay? It's not an random process, but there is it's not a mathematical process. Well, I'm not sure whether people know about the control theory pole placement problem. This is a partial pole placement and first order pole placement problem is very popular in control theory. By the way, I have a book in control theory also, Numerical Methods for Control System Design Analysis. So some of this stuff will be there. You can have a look. And if you want a copy, I can send you the copy. But here we did not need that book. Okay, now the problem gets a little harder. It is not only enough to solve this eigenvalue problem, but the two matrices F and G, those are unknown matrices, right? We have to construct them in such a way that the bad eigenvalues are replaced by good ones, while the good ones remain unchanged, and the corresponding eigenvectors. But these two matrices F and G, they call feedback matrices. It is not enough just to construct them. You have to construct them in such a way that they have some good properties. What are the good properties? One of the properties is that the matrix F and G should have norms as small as possible. Why? Because if you have a large feedback matrix, then engineers cannot work with a large matrix. It is a practical impossibility. You need a large number of sensors and actuators. You know what are sensors and actuators are. So those things, it's not available. So from the practical point of view, it's important that F and G have norms as small as possible. And this is an optimization problem. When we're talking about as small as possible, that means we are talking about minimization problem. Okay? And the second one is that the eigenvalues of the closed loop pencil will be as well conditioned as possible. Why? The eigenvalues are known to be very susceptible to small perturbations. Very susceptible. Unless they are the eigenvalues of a symmetric matrix. In general, the eigenvalues are very susceptible to small perturbations in the data. And in engineering, there is always possibility that there are some perturbations. So the eigenvalues, those F and G have to be constructed in such a way, the eigenvalues, the condition number of the eigenvalues is as small as possible. Again, this is an optimization problem. So from engineering, we are now in mathematics. Okay? The whole thing is now mathematics. It's numerical linear algebra. Any question? Well, the one that, so we have some name. So if you want the feedback matrix F and G have the norm as small as possible, it's called minimum norm problem. And if you want the eigenvalues to be well conditioned, it's called robustness of the scheme. Okay. Now, I might not have time to show you the details, but I'll show you the solution of the original problem. Then you can talk about the robustness. Okay? So remember, oh God, I don't know what is happening. Okay. So remember that we have to construct the matrices F and G in such a way that we have only few eigenvalues which can be computed at our hand, and the corresponding eigenvectors. We don't know the remaining 2n minus p eigenvalues and the corresponding eigenvectors. We don't have any idea. We have to solve the problem using only those few eigenvalues and the corresponding eigenvectors. That's the challenge here. But at the same time, we have to prove that those eigenvalues and eigenvectors do not change. The 2n minus p eigenvalues and eigenvectors do not change. So here is a very simple solution. If we say that if we construct the matrix F and G in this way, where lambda 1 is the diagonal matrix of the let me show you the thing. Yeah, lambda 1 is the diagonal matrix of the eigenvalues to be reassigned. So those are the eigenvalues which need to be changed. And x1 is the corresponding eigenvectors. And lambda 1 prime, it's type is a small capital lambda 1 prime, is the diagonal matrix of the eigenvalues to assign. And x2 is the corresponding eigenvector, and so on and so forth. So using them, we have to solve the problem. Yeah. Oh God. I don't know what is happening. Okay. So, the first part is said, okay, if we construct our f and g in this way, knowing only the eigenvalues that can be computed and the corresponding eigenvectors. So x1 and lambda 1. Lambda 1 is the diagonal matrix of the eigenvalues that needs to be changed, and x1 is the corresponding eigenvectors. And P is any arbitrary eigenmatrix. So we can show that if I construct my f and g in this way, then there will be no spillover. That means those 2n minus p eigenvalues and eigenvectors will remain unchanged. And we can prove this result mathematically. So if we construct f and g in this way, then we can prove that there will be no spillover. There is a mathematical theorem, and it is not an easy proof. So I'm not going to talk about it. It's a story about this proof. I'll tell you the story later. Now, okay, here in the first part, so we proved the no spillover part. But then, another part of the problem still remains. How do you reassign the bad eigenvalues to the good eigenvalues and the corresponding eigenvectors? There are two parts. The first part is the no spillover part, and we took care of that very well. Second part is the reassigning the eigenvalues that need to be reassigned. And it turns out if you do that away, so there is a vector P was arbitrary. Now the question arises, how do you choose that matrix phi so this will happen? And you can see that we can construct the matrix phi in this way, that will happen. So the whole story is here that we can solve the problem, this difficult problem, by using only the few eigenvalues and eigenvectors that can be computed. And mathematically can prove that remaining 2n minus p, remaining large number of 2n minus p eigenvalues and eigenvectors will remain unchanged. That is the most important thing. Okay? So what's the time? How much time we have? $15 minutes. Okay, so the next part of the talk of this mechanical feedback problem is kind of hard because we need a lot of numerical optimization techniques to do that. So I'm just going to skip it. I'm going to the second part of the talk. Okay, that will be easy to understand. You know the problem is how to compute the solution in such a way that the eigenvectors of the closed loop pencil will be as well conditioned as possible. Okay, eigenvalues will be as well conditioned as possible. That was the hard part because we don't know them. If we had known them, then we could have computed the gradient formula and it would be piece and cake, but we don't know them. That was the hard part. And it took a lot of effort to solve that problem. Actually, I was not as smart. A Chinese mathematician, he joined me to solve this problem. Okay. very, very, very young, very bright man. I just came back from China 2 weeks. I was in China for 2 weeks. Some of the people are very smart there. They don't speak good English, but they're very smart. And before I go to the other part, let me tell you a story about how they solved the first part, the solution that I showed you. I was working with two scientists at the University of Adelaide in Australia. One of them is a mechanical engineer. Unfortunately, he passed away. Another one is a computer scientist. And we came to a solution, but we knew that the solution is the right one, and it can be shown that there'll be no spillover. But that part was the mathematical part. This was the hardest part. One was engineer, another was computer scientist. So they put the burden on me. So you are a mathematician. You solve this problem. And I lost few nights of sleeps worrying about that problem. One day, 3 o'clock in the morning, I got some ideas. I immediately called my colleagues. Oh, I have solved the problem. They said, Biswa, you are crazy. Go to the bed. It's 3 o'clock in the morning. I went to the bed, but I could not sleep. So 5 o'clock in the morning, I ran to the department, 5 or 6 o'clock, and then started showing them the solution. The engineer said, you're crazy. This is absolutely impossible. But I proved it. It is mathematical proof. Anyway, so let me go to the second part. So I always try to tell some stories to the people so that it becomes more interesting. Otherwise, who cares for mathematics, engineering, Okay, this is the finite element model updating part. Well, the model lambda square m plus lambda c plus k is a finite element model because this model was generated by using finite element techniques. That's it. That's why it's called finite element model by engineers. Finite element doesn't have much to do here because it was generated from the original partial differential equation by using finite element techniques. Okay, it's a well-known technique. Now, this problem arises very often in aerospace engineering. When a company like Boeing or Airbus, they make a plane, there is always a protocol structure. Well, here's a plane. Corresponding to that plane, there's a finite element model. It's like, suppose you build a house, right? Before you build a house, there's a blueprint of the house. And you follow the blueprint to build the house. But even after following the blueprint, house may not be exactly what the blueprint says. So that's what a plane has been made, built, following the blueprint, but it may not be the same one. So how do you authenticate that? The plane has already been made. You cannot change that. So what happens? You have a corresponding finite element model, theoretical model. So the idea is how to update that model in such a way that the few eigenvalues and eigenvectors, which they call frequencies in mode sets, will be computed, and they will be replaced by the bad ones like we did in such a way that there will be no spillover. So the problem is the following. So you you compute a small number of eigenvalues and eigenvectors experimentally from a realized practical structure like Boeing 777. And actually, I have seen them hammering to get the frequencies in mode sets. We call eigenvalues, they call it frequencies. Okay? And then, these major eigenvalues and eigenvectors are then compared with the corresponding one from the finite element model. And frequently, there is a disagreement. They don't match. So what do the engineers do then? So the vibration engineer then faces the problem of updating the finite element model with minimal changes so that the updated model has the following properties. The major eigenvalues and eigenvectors are reproduced by the updated model. The model was there, but that model was not the right model. So they want to make it, they will correct the model. The way they do that, they have computed few eigenvalues and eigenvectors from the existing structure, for example, Boeing 777. And then they compare them with the ones that from the finite element model, how they see how they're different. And they replace the ones, and so the major eigenvalues and eigenvectors are reproduced by the updated model. The remaining eigenvalues and eigenvectors do not change. The same problem that we are talking about. But the other problem, we are using control force, there is no control here. Okay? And the structural property, the most important is that, which was not a requirement of the first problem. Here, very important, that finite element model has some nice structural properties because the matrices are symmetric, some of them positive semi-definite. M is symmetric positive definite in practice. K is positive semi-definite. C something is a damping matrix, you don't know how it looks like. Okay. So those nice properties, and they are sparse. The K matrix is very sparse. There are only few non-zero entries. So those nice properties, symmetry, sparsity, have to be preserved. So that's what the challenge of the problem is. And this is an important problem. I have worked with Boeing company for several years on this problem. Okay, we have some solutions, but still a long way to go. Very important problem, very practical problem, but it's not an easy problem. You understand the problem, right? I think I'll stop here, and thank you for your attention.
Thank you very much, Biswa. ¿Tienen preguntas? ¿Alguna pregunta sobre el tema? ¿O sobre cualquier otra cosa? Úrsula, ¿no? Eres la experta.
It's a well understood talk. Everybody understood it.
Yeah. ¿Alguna pregunta? Actually, I have a question.
Sure.
But that's a modeling one. In the first...
Where did it go?
First transparency
Yeah.
work. You have I mean, the way that you propose the model to find the control, it's a very special one, right? And what I don't understand, what is the motivation to propose the control in that way? Because I've seen that it's very special one because you use the F and G matrices.
Yeah, feedback matrices.
Yeah, feedback matrices. So what is the motivation behind that modeling proposal?
In control theory, it is well known that if you have a system which is, say not stable, okay, so you use feedback matrices to make the system stable. So that means, a simple problem. Say, suppose you consider first order differential equation x dot t equal to axt plus bu. where B is the control matrix, A is the control vector. You choose the control vector U in such a way that the closed loop pencil will have a desirable property. So this is the motivation. We generalize that to the second order case.
Yeah, I understand that. Seems to me that you can also
You have another way
try
do
to
that,
solve
yeah.
this problem using, for instance, a joint equation method and large scale optimization.
Yeah, well, this is
It's an alternative, right?
The problem here is that to maintain this no spillover, that's the problem. That's the hardest problem.
That's the problem.
And that has to be done mathematically because you don't know them.
Thank you. ¿Alguna otra pregunta?
Last semester, we had a project on control theory in which we modeled an earthquake in a building. We used similar equations to yours. However, we did not use the quadratic eigenvalue formula. We went into like a controller method.
What method?
Like we use control like PYD and all of that to control the building. However, we had a question since in our case, our perturbance force was the earthquake itself. And to search the harmonic frequencies of the earthquake that match the building, in our case, we could calculate them based on the input earthquake. But in your case, my question is, you generalize like in which cases the harmonic frequency might occur in the building, or do you have like a range on such a
Well, in general, there is a range. Frequency range, where you want to keep the eigenvalue in that range. Okay, and the range depends upon the practicing engineer. They, for example, as you said, the earthquake. Okay, so a practicing engineer, they know what ranges of eigenvalues should be there, so there will be no earthquake. But this is all ad hoc thing. This is not a mathematical thing. This is not a science. This is an art.
Okay.
Okay. Yeah. But that's how it is.
Okay.
That's a good question, though.
¿Alguna otra pregunta? Ok, ya se animó Úrsula.
Well, it's very nice to meet you, Biswa. Well, I'd like to ask you something related to neural networks. You talk about the Tacoma Bridge, and
What's that?
Tacoma Bridge.
Tacoma Bridge, yeah.
The Tacoma Bridge. Have you tried to use physical informed neural networks to solve these ordinary or partial differential equations?
I didn't answer the question.
No?
Say it again. I didn't
Okay.
understand.
Have you tried to use physical informed neural networks to solve this kind of? No. You have not. Okay.
This is just control theory point of view.
All right.
Yeah.
And the other thing that I'd like to say.
Neural network would be a good idea to do that. We have not done that.
Okay.
Maybe I can learn from you.
Yeah, I can show you what I did.
I'll be
It's
talking
very
about
small.
neural network in my course tomorrow.
Okay. The other thing is that, well, I like your book, and thank you for writing that book. It's very nice, the linear algebra book.
Yeah, he can give you an access.
I have
you have
a hard copy.
Oh, good,
Yeah.
good. Good for you.
Thanks.
Yeah, I love my book.
Bueno, ya ni modo. Ok, bueno, si gustan, yo tengo el libro de Biswa, electrónico, pues nada más me dicen y me dan su correo electrónico y les puedo proporcionar una copia. Sí, también dicen que está libre en la red. Bueno, ustedes ya saben, ¿no? Son profesionales. Ok. Sí, cualquier material que quieran y que yo les pueda proporcionar, bueno, ahí estamos, al pendiente. Si les parece bien, como el profesor ya está muy cansado, pues terminamos aquí y pues tenemos un poquito de tiempo para relajar antes de ir a comer, ¿no? Bueno, pues les agradecemos su presencia y vamos a darle un aplauso final, profesor. Dice que se quiere tomar una foto con ustedes. Entonces vamos a preparar para tomar una foto. Yo creo que aquí mismo, ¿no? Sí.